this is our AP Chemistry Chapter 4 lesson video, Part 2, and we're going to cover Section 4.3 and 4.4. So we're going to continue talking about solutions, acids and bases, net ionic equations, and that type thing. But we're also going to cover something that I may or may not have had time to get to in Honors Chem. It just depends on what year you had me, and that is oxidation reduction reactions. Okay, so that's very important. So if you remember everything about acids and bases and you want to skip through to Section 4.4, that we might not have gotten to in Honors. Again, it just depends on what year you had me. So acids and bases are also common electrolytes. Acids are substances that ionize in aqueous solutions to form hydrogen ions. And hydrogen ions consist of only one proton, so acids are often called proton donors. Okay, so we talked about that back in Honors when we learned about acids and bases. So monoprotic acids contain one ionizable hydrogen. So like HCl has one hydrogen that it can produce when it separates into ions. Diprotic acids contain two ionizable hydrogens, so like H2SO4. And triprotic acids contain three ionizable hydrogens, like H3PO4. Most multiprotic acids only lose one hydrogen to a reasonable extent. So in other words, even though it's H3PO4, each one of those is mainly going to lose one hydrogen. The other two, they'll lose to much smaller extent. So what are some properties of acids? Well, acids taste sour. Some acids also contain hydrogens that will not ionize. And normally the hydrogens that will ionize are listed at the front of the chemical formula. Oh, there's a typo. That should say front. Okay, so if you have acetic acid, a lot of times it's written H, C2H3O2. So this is your ionizable hydrogen, and these three are not ionizable. They are part of the polyatomic ion. Sometimes the hydrogen that will ionize is listed at the end of a COOH group. So if you look at the two formulas, these are actually the same thing. They're both acetic acids, just written in two different ways. This one you have your ionizable hydrogen first, and acetate is written second. This one is kind of trying to show you the bonding, and the fact that it's saying C is bonded to the two O's and the H. This is actually your ionizable hydrogen here, and these are not. Okay, so you'll see acetic acid written both ways. But again, only one hydrogen is ionizable. Bases, on the other hand, taste bitter. Bases are substances that accept or react with hydrogen ions. Bases produce hydroxide ions when they dissolve in water, so they produce OH negative. Bases do not have to contain the hydroxide ion. So for example, NaOH is a base. It is going to literally split up into Na positive and OH negative. So that's how it produces the hydroxide ion, is just by splitting apart. Whereas NH3 is also a base. However, it does not have OH in it. So where is the OH coming from? Well, when NH3 reacts with water, NH3 takes one of the hydrogens from water. So it becomes NH4 positive. Well, once water loses a hydrogen, it becomes OH negative. So see, it's still producing OH negative, it's just not coming off of the NH3. Okay, and NH3 is our most common weak base. There are many other weak bases, but that's our most common one. Lots of weak bases also contain nitrogen, because nitrogen has that lone pair of electrons that can then react with the hydrogen from water. So strong versus weak. Strong acids and bases are strong electrolytes, so they fully ionize in solution. Whereas weak acids and bases are weak electrolytes, so they only partially ionize in solution. So see, a strong acid, pretty much all of them are going to split apart into their ions. Whereas a weak acid, if you look, only a couple of them split up into their ions. Most of a weak acid or base will remain in its neutral molecular form. You need to memorize the strong acids. So we have hydrochloric acid, hydrobromic acid, hydroiodic acid, chloric acid, perchloric acid, nitric acid, and sulfuric acid. Okay, so there are 7 of them, and so you just need to know these. So if it's an acid and it's not one of these, it's considered weak. You need to memorize your strong bases. So our strong bases are group 1 metal hydroxides. So you have Li, Na, K, Rb, Cs. They're all bonded with OH, hydroxide. and then your heavy group 2 or alkaline earth metal hydroxides. So your heavy ones are the ones that are lower on the periodic table. Okay, so you're going to skip past beryllium and magnesium, so it's calcium, strontium, and barium. So all of these will fully break into ions. So that's why I'm saying in the previous video, if you form one of these, even though our solubility rules say that hydroxides tend to be insoluble, these will be soluble because they're a strong base. Now these you don't have to worry about remembering because what's one of our important solubility rules? That alkaline metals are soluble. So you don't have to worry about these, but it's these three down here that you need to remember are going to be soluble. So let's look at our first sample exercise. It says the following diagrams represent aqueous solutions of 3 acids, HX, HY, and HC, with water molecules omitted for clarity. Rank them from strongest to weakest. Okay, so we'll start with our strong and we'll work to our weak. Okay, well the strength of an acid depends on how much separates into ions. So the strongest acid will have the most of them that have split. So if I look, this one has quite a few that are still together. This one, they are all split. So that means HY will be my strongest. All right, HY is going to be the strongest because they have all fully split up. HX and HZ have some that have stayed together. Okay, so now we just have to look at who split up the most. So on HX, I have 2 that have split. On HZ, I have, let's see, 2 that have split. So I need to look at who stayed together. On HX, I have 1, 2, 3, 4, 5, 6 that have stayed together. On HZ, I have 1, 2, 3, 4, 5 that have stayed together. Oh, and I actually had 3 that split. Sorry, I miscounted there. So out of these, who's stronger? Well, HZ had 3 split up, whereas HX only had 2. So HZ would be in the middle, and then HX, because it only had 2 that split, it would be the weakest. Okay, so sorry about that. I totally miscounted there. So this one had 2 split up, and 1, 2, 3, 4, 5, 6 stay together. This
Mr. Hope, you have a moment if you'll come to the cat chat,
and
please.
1, 2, 3, 4, 5 stay together. All right. So let's move on. Don't forget to be trying some of these on your own. All right. So it says imagine a diagram showing 10 sodium ions and 10 hydroxide ions. If this solution were mixed with the one pictured on the previous question, so I brought that same picture down for HY. So here's my HY. What would the diagram look like that represents the solution after any possible reaction? And then it tells me the hint that H plus will react with OH minus to form water. Okay, so in other words, I need to put what this diagram would look like after I mix 10 sodiums and 10 hydroxide ions. All right, so I know these positive ones are hydrogen. All right, and I know these negative ones are technically just Y because it didn't tell me what they are. Okay, so I know that sodium ions are soluble, so that means it's not going to bond with anything. So there will still just be 10 sodium ions floating around. Okay, it's not going to bond with anything. However, it's told me that H plus will react with OH minus. Well, how many OH minuses am I adding? I'm adding 10. Okay, so that means we'll get, I'm just going to cross out each hydrogen it will bond with. So we'll get 1 water molecule, 2, 3, 4, 5, 6, 7, 8 water molecules. Okay, so all of those hydroxides are going to bond with all the hydrogens that are available. But I'm only making 8 water molecules, so my other 2 hydroxide ions will have to remain as ions. So I'll have 2 hydroxide ions left over. Okay, because see, there's only 8 hydrogens for them to bond with. All right, and then my negative Y ions aren't going to bond with anything. Remember, this is a strong acid, so it's going to fully break up. So I will also have 8 Y negative ions, just like that. Okay, and the reason again that the sodium is not going to bond with the Y negative, because that's a common mistake that I would see on this type of question, is that sodium is soluble, so it's not going to bond or precipitate with anything. All right, so let's move on. Hopefully you got that one right. Okay, and so see, there's what I would have left. All right, so strong versus weak electrolytes. So our strong electrolytes, Ionic, all of them are strong electrolytes. None of them are weak electrolytes, and none of them are non-electrolytes. Molecular, your strong acids or strong bases are strong electrolytes. Weak acids and weak bases are weak electrolytes. Anything else is a non-electrolyte. Okay, and remember that's just about how well it can conduct electricity. So it says classify the following substances as strong, weak, or non-electrolyte. Okay, so I'll just put strong, weak, and non. Alright, so we have CaCl2. Well, I can immediately tell this is ionic because it's a metal and a non-metal, so it's going to be strong. HNO3, that is a strong acid, because remember, you got to learn the 7 strong acids. So that is a strong electrolyte. C2H5OH, that is ethanol. Okay, it's not an ionic compound because it's not a metal and a non-metal. It is not a strong acid or strong base. It is not a weak acid or weak base, so it is just a molecular compound. All right, then it says HCOOH, and then it says it's formic acid. Okay, well I know my 7 strong acids, and formic acid is not one of them. So that means it must be a weak acid, which falls under weak electrolyte. All right, and then our last one is KOH. So this is a strong base. It is also an ionic compound, metal and non-metal. So it is going to be a strong electrolyte. Okay, so like I said, strong include all ionic compounds, your strong acids, your strong bases. Weak include your weak acids and weak bases, and non-electrolytes include all other molecular compounds. Okay, so if you haven't tried it, try this one on your own. It says, consider solutions in which 0.1 mole of each of the following compounds is dissolved in 1 liter of water. So we have calcium nitrate, glucose, sodium acetate, and acetic acid. Rank the solutions in order of increasing electrical conductivity based on the fact that the greater the number of ions in solution, the greater the conductivity. Okay, so here we have low conductivity, and we're going to high conductivity. Okay, and so conductivity is based on the number of ions. Well, first, I can see this is ionic. It's going to break up into ions, so this is probably going to be closer to my high. Glucose is molecular. It's not going to break up into any ions, so it would have the lowest conductivity. Okay, it's also not a weak acid, weak base, anything like that. All right, I have sodium acetate. That's ionic, so it's going to break up into ions. That would be on my higher side. And then I have acetic acid. Remember, some of this will break up, but not much because it's a weak acid, so that would be my next one. All right, so now I'm down to my 2 that will fully break into ions, so I need to see how many ions am I going to get. Well, for calcium nitrate, every one that breaks up, I'm going to get a calcium and 2 nitrates. So I'm going to get 3 ions for every one of those that breaks up. For sodium acetate, remember, don't let the fact that they wrote it differently throw you off. You're going to get 2 ions. You're going to get sodium and acetate. So when these break up, you just get less ions. So my sodium acetate would be next, and then my calcium nitrate, because I'm going to get 3 ions for every one that breaks up, would have the highest electrical conductivity. Okay, so again, it's just based on the whole electrolyte, weak electrolyte, strong, non-electrolyte stuff. All right, so neutralization reactions. When a solution of an acid and a solution of a base are mixed, a neutralization reaction occurs. The products of the reaction are water and a salt. It doesn't have to be NaCl. It's just the cation and anion that are left over once the hydrogen and hydroxide form water. A salt is any ionic compound whose cation comes from a base and whose anion comes from an acid. So it says, write a balanced equation for the reaction between aqueous solutions of acetic acid and barium hydroxide. Then write the net ionic equation. So this is where you have to be careful with those weak acids, weak bases. Okay, so let's try this one together, and then you can try the next one on your own. All right, so so it says we have aqueous solutions of acetic acid. So I have CH3COOH. That's aqueous. And of my barium hydroxide. So barium's Ba, it's positive 2. Hydroxide's OH negative, so I'm going to need 2 hydroxides, and that is also aqueous. So remember, in a neutralization reaction, your OH and your H are going to form water. So I'm going to have H2O. Water is a liquid. I mean, it can be a gas, but it shouldn't be a water vapor in this case. And now barium is going to bond with acetate. And y'all, you're more than welcome to rewrite this like this if you would prefer, and take your H and OH and make water and your barium and acetate and bond it together. It doesn't matter how you write it. So barium's positive 2. My acetate is negative 1, so I'll need 2 acetates. All right, and then one of our solubility rules is that acetates are soluble, so this will also be aqueous. All right, and so does it ask me to balance it? Yep, balance. So let's balance this thing. So here I have 1 acetate, but here I have 2 acetates, so I'm going to put a 2. I have 2 hydrogens, 1 barium, 1 barium. Oh, sorry, I didn't count my hydroxide hydrogens. I have 4 hydrogens, so I needed 2 right here, and then 2 oxygens, 2 oxygens. And the reason I didn't count these hydrogens or oxygens was I counted them in the acetate. All right, so this is where you have to be careful, because when you write the net ionic equation, it's very easy for people to say, okay, well, acetate's aqueous, is still aqueous, hydrogen's aqueous, it became liquid, barium's aqueous, it's still aqueous, hydroxide's aqueous, it became liquid. So you just want to pull down the hydrogen, the hydroxide, and the water. But the problem is, this is not a strong acid. This is a weak acid. So we treat it as if it was a solid, okay, because most of it's not going to break up. So if we're treating this as a solid, then you can see the only thing that's actually aqueous on both sides is your barium. So that's the only thing I can take out of my equation. So I still have to keep this. And y'all, even though I say we're treating it as a solid, you still call it aqueous. Okay, so we have our acetic acid. We have now our 2 hydroxides. We're going to make our 2 liquid water molecules. And then we have our 2 acetate ions left over. Okay, now because once I pulled out barium, they all have 2 coefficients. Remember, we always like it to be in the lowest ratio possible so you can remove all of your 2's. Okay, and so see, this is why people miss this type, because once they see acetic acid as aqueous, they want to pretend like all of it splits up, and then they want to take it out of the net ionic equation, or at least the acetate part they do. Okay, so just be careful of that when you're trying the next one on your own. Okay, so just pause the video. You try the next one. Just hint, hint, carbonic acid is a weak acid. All right, I'll assume you've tried it. Let's look at it together. So it says, write a balanced equation for the reaction of carbonic acid, which it was nice enough to tell you is H2CO3. However, you should have been able to easily figure that out yourself. And potassium hydroxide. So potassium's K positive, hydroxide's OH negative, so I don't need any subscripts. All right, so I know that my OH and H are going to make water. So my H and my OH, they're going to make water, which is a liquid. And so K and CO3 have to bond together. So K positive, CO3 negative 2 means I need 2 Ks. And so remember, one of our important solubility rules is alkali metals are soluble. So this will be aqueous. All right, so let's balance this thing. So I have 1 K, 2 Ks, so I need a 2 here. I have a CO3, a CO3. I have 2 4 H's, so I need a 2 right here. And then I have 2 oxygens. Okay, so here is my balanced equation. So remember, we have to remind ourselves, this is a weak acid. It is not going to fully dissociate into ions, so we treat it as if it's a solid. So when I look, I can see the only thing aqueous on both sides are these K's. That's it. Everything else I have to keep. Okay, so I bring down my carbonic acid. hydroxides. Don't forget to use those coefficients. I'm going to bring down my 2 water molecules because those hydrogens and hydroxides formed a liquid. And I'm going to bring down this carbonate ion. Just like that. Alright, so hopefully you got that one right. Like I said, net ionic equations really are only tricky when you have that weak acid or weak base, because you just want it to be aqueous on both sides, and then it's just not. Alright, so last thing we have to talk about is gas formation. Okay, and we did talk about this in honors. So the sulfide ion and carbonate ion will react with acids to form gases. So you just have to be careful, and these are just 2 scenarios you're just going to want to memorize. Okay, so when we have sulfide and an acid, you're going to make hydrogen sulfide gas. So you just need to remember this is a gas. Alright, and then if you form carbonic acid, which is H2CO3 as a product, it's automatically going to turn into liquid water and carbon dioxide gas. It just automatically will dissociate into that. So if you write that as a product, like if you do a double displacement reaction or something like that, and write it as a product, you need to just go ahead and change it to liquid water and carbon dioxide gas. And the reason that these are important is because since these are gases and this one's a liquid and a gas, they'll alter how your net ionic equation works because they're not aqueous. Alright, so let's move on to oxidation reduction reactions. So again, depending on what year you had me, this may or may not be new information. So oxidation reduction reactions, or redox reactions, are reactions in which electrons are transferred between reactants. So oxidation is loss of electrons, and reduction is gain of electrons. The easy way to remember it is oil rig. Oxidation is loss, reduction is gain of electrons. Oxidation and reduction always occur together, because if something loses electrons, somebody else has to gain them. They don't just fly off into space. So the rules for writing oxidation numbers. For an atom in its elemental form, the oxidation number is always 0. So like if it just says sodium solid is 0. Don't forget, some of our elements are diatomic, so like F2 gas is 0. For any monatomic ion, the oxidation number equals the charge. So for example, if we had magnesium nitride, we know magnesium's positive 2, nitrogen's negative 3, and then we cross our charges to make magnesium nitride. So the oxidation numbers are just the charges. The oxidation number of hydrogen is usually positive 1, so like in HCl it's positive 1, except when bonded to, when bonded to nonmetals, but except when it's bonded to a metal. Sorry, I thought I had a typo there, but I was just not reading it correctly. So it normally is positive 1, but if it's bonded to a metal, so see like we have lithium hydride here, it's a negative 1. Okay, so normally it's positive 1, but once it's bonded with a metal, it is negative 1. The oxidation number of oxygen is usually negative 2, except in the polyatomic ion peroxide, which is O2 with a 2 negative, where it is negative 1. And then the oxidation number of fluorine is negative 1 in all compounds. All other halogens have an oxidation number of negative 1, except when combined with oxygen in oxyanions. Okay, so here fluorine's negative 1, here bromine's negative 1, but here oxygen is negative 2. So to have a negative 1 charge overall, fluorine actually has to be positive 1. So when you have a halogen with oxygen, oxygen's negative 2 oxidation state is what you use to figure out what the halogen would be. The sum of the oxidation numbers of all atoms in a neutral compound must be 0. So here I have P2O5. I know O is negative 2, and there's 5 of them, so that's negative 10. So since there's 2 P's, P has to be positive 5, because negative 10 and positive 10 give me 0. However, if it's a polyatomic ion, the oxidation numbers have to equal the charge. So again, I know oxygen's negative 2, and there's 3 of them, so that's negative 6. So normally we'd say, oh, well then carbon has to be positive 6. But we need a negative 2 charge, so carbon is actually only positive 4. Okay, so that's where you have to be careful. We're used to always trying to cancel charges, but if it's a polyatomic ion, the charges don't, the oxidation numbers don't need to cancel necessarily. They have to equal the charge. All right, so let's look at this first one together. It says determine the oxidation number of sulfur in each of the following. Well, we might as well just determine all the oxidation numbers just for practice. All right, so we know hydrogen is normally +1. Since there's 2 of them, that's +2. So sulfur has to be -2. So sulfur would have a -2 oxidation state there. For part B, it's just sulfur. Everything in its elemental form is 0. So sulfur would have a 0 oxidation state there. Here, we know chlorine is a halogen. It's -1, but there's 2 of them, which is -2, so sulfur must be +2. And then here, we know that sodium is +1, and we know SO3 is going to be -2. That's important to know. So my oxidation states must equal -2 there. Well, we know oxygen's -2, but there's 3 of them, so that's -6. So in this case, sulfur would need to be +4. Because see, then a +4 and a -6 gives me -2, and then the 2 positive sodiums cancel it out to make it 0 again, because the whole compound is neutral. All right, last one, SO4 -2. So we know oxygen's -2, and there's 4 of them, so that's -8. So normally sulfur will be +8, but we need a -2 charge left over, so it's only +6. Okay, so the same element can have many different oxidation numbers or oxidation states. But the important thing not to forget is when an element is completely alone, its oxidation number is always 0. That's easy to forget. All right, so it says, what is the oxidation state of each element in the following? Okay, so make sure you pause the video and try this, and then we'll look at it together. So I know oxygen's -2, but there's 5, so that's -10. So P has to be +10, but there's 2 of them, so they will each be +5. So P is +5, O is -2. All right, here, normally hydrogen's +1, but it's bonded with a metal. So sodium will be +1 and hydrogen will be -1. Remember, hydrogen's normally +1 unless it's bonded with a metal. All right, so here, we have to have a -2 charge overall. Oxygen's -2, but there are 7 of them. So that's -14. To get a -2 charge, I need +12. But there's 2 of them, so they will each be +6. Okay, and y'all, you've got to get to where you can do these pretty quickly. All right, here, Br is a halogen, so it's -1. There's 4 of them, so 10 has to be +4. Then our last one, barium is +2. Now normally oxygen's -2, but then that would be a -4 and a +2. That doesn't cancel out to give me 0. That makes me realize, oh, this is actually peroxide. So remember, peroxide's O2 with a -2, where each oxygen is actually only -1. Okay, so that's how you can recognize that something is a peroxide if they don't actually tell you the name. All right, so hopefully you got those right. So let's start using this in the form of a reaction, now that we know how to assign oxidation numbers. So many metals undergo displacement reactions with acids to form salts and hydrogen gas. Write the oxidation numbers for each element to determine which element is oxidized and which one is reduced. So for example, magnesium by itself is just 0, hydrogen's +1, Cl is -1. Now magnesium's bonded, so we know it has +2 charge, so +2 oxidation state. Chlorine's -1, and now hydrogen is alone, so it's 0. So if you notice, magnesium has gone from 0 to +2. That means it has lost electrons, so we say magnesium is oxidized. So since magnesium goes from 0 to +2, it's oxidized. And then remember, oxidation and reduction always have to happen together. So hydrogen went from +1 to 0, so it became more negative, or it gained electrons. So remember, reduction is gain of electrons. So since hydrogen goes from +1 to 0, it is reduced. All right, so let's look at one together. So it says, write the balanced equation and net ionic equation for the reaction of aluminum with hydrobromic acid. Hang on, let me see if there's a part 2 to this, or should I erase it when I'm done? Okay, we're not going to do anything with oxidation reduction on mine. All right, so we have the full reaction. So aluminum is just Al, it's a solid, and hydrobromic acid. So hydrobromic acid is HBr. And remember, acids are aqueous unless otherwise stated. So what's going to happen is, remember, aluminum is going to bond with bromine because aluminum is +3, bromine is -1. So I'm going to need 3 bromine. And then when hydrogen is by itself, it's H2 and it's a gas. All right, and then our aluminum bromide will remain aqueous for that part. Okay, so the important thing to remember is that when hydrogen is by itself, it is a gas. Sorry, let me get caught up in all my things here so I can see when I'm stopping. All right, let's see. Okay, all right, I see where we're stopping now. All right, so next I need to balance. So I have 1 Al, 1 Al, 1 H, 2 H's, so I'll put a 2. 2 Brs, 3 Brs, that means I need to turn them both into 6. That means I now have 2 aluminum, so I need a 2. I now have 6 hydrogens, so I need a 3. Alright, so then it says write the net ionic equation. Okay, well, I can see aluminum was solid, it's now aqueous. I can see hydrogen was aqueous, it's now a gas. I can see bromine was aqueous and it's still aqueous. So all I can get rid of on this one is the bromine. Okay, so I keep my 2 aluminum solid. I keep my 6H plus aqueous. I keep my 2 aqueous aluminum ions. And I keep my 3 hydrogen gas. Okay, so remember, you can only leave out spectator ions, which are aqueous on both sides. Alright, so you try the next one. I believe the next one will have some, there we go, oxidation and reduction question in it too. Okay, so I'll assume you've tried this, so let's look at it together. So it says write the balanced and net ionic equation for the reaction between magnesium and cobalt-2 sulfate. Okay, so we have magnesium, it's just a solid because it's a metal, and we have cobalt-2 sulfate. So cobalt-2 means cobalt's +2, sulfate means SO4 is -2, and we have aqueous for that. Alright, so magnesium is going to bond with the SO4. So magnesium +2, SO4 -2. That will also be aqueous because your sulfates tend to be aqueous. There are some exceptions, but magnesium is not one of them. And now cobalt will be a solid because it's by itself. Alright. So, let's balance. We have 1 Mg, 1 Mg, 1 CO, 1 CO, 1 sulfate, 1 sulfate. Well, that was easy. Now let's write the net ionic. Okay, well I can see that magnesium was solid, now it's aqueous. Cobalt was aqueous, now it's solid. The only thing that remained aqueous on both sides is sulfate, so I can get rid of sulfate. Okay, so I bring down my magnesium solid, my cobalt ion, which was aqueous, making my magnesium ion, which was aqueous, and my cobalt solid. So then it says, what's oxidized and reduced? Well, this one should have been super easy for you. Here is magnesium in its elemental form, so it's a 0. This one, it has the charge for you, it's +2. This one has the charge for you, it's +2. This one has cobalt in its elemental form, so it's 0. So let's look at what's happening. So magnesium went from 0 to a +2, which means it lost electrons. So oxidation is lost, so magnesium was oxidized. And then cobalt went from +2 to 0. So that means it gained electrons. Well, reduction is gained, so cobalt was reduced. And that's all you have to do. Now, not all the time are the reactions going to be this easy to be able to write the oxidation states. But in this case, it was that easy. All right. So hopefully you got that one right. So last thing we have to talk about in this video is activity series. So a list of metals arranged in order of decreasing ease of oxidation is called an activity series. Active metals are at the top of the series and are most easily oxidized. Noble metals are at the bottom of the series and are not very reactive. So we know noble gases are called noble because they're not reactive. So noble metals are also not very reactive. So here's the important part of this slide. So because we're going to need this a lot, I'm just going to kind of abbreviate it over here. So any metal, so in this case we're talking about the solid, any metal can be oxidized by the ions of the elements below it. Okay, so I find my solid metal, and any ion below it will cause a reaction to happen. Any ion above it will not let it react. Okay, so let's say we're asking, can barium metal react or be oxidized by sodium ions? Okay, so I find my barium metal. So here's my solid. Sodium is underneath it. So the barium solid will be oxidized by the ion below it. So that means the sodium ion will react with barium. On the other hand, if I said, will potassium oxidize barium? Well, there's my solid barium. Potassium is above it. So potassium ions will not oxidize barium solid. However, barium ions can react with potassium solid. Okay, so you find your solid, and any ion below it will cause a reaction. So it says, will an aqueous solution of iron 2 chloride oxidize magnesium metal? If so, write the balanced equation and net ionic equation for the reaction. Okay, so we have magnesium metal. That's my solid. So I need to see, is iron below magnesium metal? So here's my magnesium metal. This is my solid. Iron is below it. So that means this reaction will occur. Okay, so my answer is yes, it will occur. Well, then it says, if so, write the balanced and net ionic equation. Okay, well, we have iron 2 chloride, so Fe positive 2, chloride Cl negative, so I need a 2. We have a solution of it. And we have magnesium metal, so just solid. So remember, what that means is that the magnesium is actually going to bond with the chlorine. So iron will be left alone, so that's a solid. And magnesium, which is positive 2, will now bond with chloride, which is negative 1. And we'll need a 2, and that will be aqueous, because we know chlorides are aqueous with some exceptions, but magnesium is not an exception. All right, we actually don't have to balance, it's already balanced. And so last step is write net ionic. Well, I can easily see that chloride is my only substance that's aqueous on both sides. So I would have my iron as aqueous, my magnesium is solid, making my iron as solid, and my magnesium as aqueous, just like that. Okay, before I erase, let me click and make sure there's not a part 2 asking about what's oxidized and reduced. It does not. But if it did ask, I'm just going to throw that out there. If it did ask, I can see Fe went from positive 2 to, when it's by itself, is 0. So that was a gain. Look, oh, I erased my oil rig. That was a gain. So iron is reduced because it gained electrons. And then magnesium went from a 0, because see it's by itself, to a positive 2. So that means it lost, so it is oxidized. Okay, which the hint was also given to in the question. It says, will iron 2 chloride oxidize magnesium metal? And we've determined that yes, the magnesium is oxidized. All right, so you try the next one. All right, it says, which of the following metals will be oxidized by lead nitrate? We have zinc, copper, and iron. Okay, so I'm going to assume you paused and tried it. I'm going to write my metals down. So we have zinc, copper, iron, and we're trying to oxidize it with the lead ion. Okay, so these are my solid metals. Here, I'll even put a little solid there to remind you. And I'm trying to see which one has lead below it. Okay, so I go back to my chart. All right, so zinc is here. Lead is below it. So zinc can be oxidized by lead. Copper is right here. Lead is above it. So copper cannot be oxidized by lead. And then iron is right here. Lead is below it, so iron can be oxidized by lead. Okay, so you just got to use that activity series. So in this case, zinc and iron can be oxidized by lead. And yay, that is the end of this video. Okay, so like I said, everything from 4.3 pretty much should have been reviewed from Honors Chem, but 4.4 might have been the new topic. So just get some practice on oxidation reduction. It's not really that hard once you get those rules down about how to assign oxidation numbers, and once you remember oil rig, it's pretty easy.